Hello, and welcome to this recorded e-learning on basic FPGA architecture memory resources for the Virtex-6 device family. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the memory resources available in the Virtex-6 FPGAs. Please note that there are also corresponding slice and I/O resources as well as clocking resources, recorded e-learning modules that are available to you as well. After completing this module, you'll be able to fully utilize the Virtex-6 distributed memory, block memory, and FIFO resources. You'll also be able to use the memory interface generator, or MIG, to build a custom memory controller for your off-chip memory component. This module is a recommended part of our Essentials of FPGA Design and Designing for Performance courses. We recommend that you take the time to attend these courses to learn all the critical design considerations you must make when targeting any FPGA device. Every FPGA design needs some memory resources. This is usually accomplished by the use of on-chip block memory, commonly called block RAM. But besides this, Virtex-6 also has other memory resources. Now, block RAM is frequently used for FIFO construction, large data storage, and finite state machines. In fact, Virtex-6 also includes dedicated hardware to convert each block RAM into a FIFO. Xilinx also includes distributed memory resources which are often used for shift registers, small data storage, ping-pong buffers, and other small functions. Virtex-6 also supports easy construction of memory controllers, which allows you to integrate an external memory controller inside of your FPGA. The Memory Interface Generator, or MIG, allows you to build memory controllers that support the newest standards and supports large data storage applications. This allows the FPGA to be flexible and quickly evolve to meet customer needs of a particular application. All of Xilinx's dedicated memory resources, that is, distributed memory and block memory resources, can be preloaded with data, so when the FPGA is programmed, they already contained the memory initialized. And since these resources support both large and small memory construction, they only use the resources that are necessary for the size of memory you need to build. So they are both fast and flexible. This slide is showing you the memory options available to you with Virtex-6. There is distributed memory, which is just the LUT reprogrammed to build a little 64-bit memory or 32-bit shift register. It is very granular and can be grouped to build larger memories very easily when you use the core generator, which is a utility included within the ISE software that is used for building all memories. Distributor RAM is great for small FIFOs and other common components. On-chip block memory, often called block RAM or BRAM, is a 32 kilobit memory resource that is fast and efficient and ideal for mid-sized data storage. We'll talk more about each of these resources individually as we get further along into this REL. Large memory interfaces, or memory controllers, are also supported with Virtex-6. Historically, Xilinx has provided access to soft memory controllers, which are built with Xilinx's primary logic resources, that is, LUTs and registers. These are still supported with the core generator. Virtex-6 now supports even more of the newest memory standards. This is a very cost-effective solution for applications that require a lot of memory space. Construction of memory controllers is supported again by the MIG, and the MIG even optimizes the IOB resources for your chosen memory component. As I mentioned, the soft memory controllers supported with the MIG are designed to build a number of different types of memory controllers. These can support a number of different I/O standards, single or double data rate applications, as well as different protocols. This is accomplished with the aid of the Select I/O functionality, which allows direct connection of the FPGA to a range of different I/O standards. This assures high performance and design reliability since the pin assignments are often pre-optimized by Xilinx experts. The Virtex-6 block memory resources also included embedded error-correcting code logic that is dedicated with each block RAM. This allows you to save CLB resources by including this functionality as part of the block RAM resource. Distributed RAM is another functionality of the lookup table. Each LUT can be reprogrammed to implement a tiny 64-bit RAM. While most customers do not use this resource, many DSP designers do, so it's a good feature to be aware of. Many DSP designers will use the Xilinx system generator to build their DSP functionality. In general, you should target the block RAM over the distributor RAM. The reason is that block RAM is a lot bigger and dedicated in the silicon. You can always use another LUT for combinatorial logic, but if we fail to use a dedicated resource, such as the block RAM, it'll be wasted. The distributed memory is available in 50% of the slices, which is actually irrelevant since the implementation tools will move your logic around so it can be accessed when needed. The distributed RAM can build single-port, dual-port, or even multi-port memories when built with the core generator. Likewise, the LUT can be programmed as a 32-bit shift register. Distributed RAM is useful for building coefficient storage, small data buffers, small finite state machines, and small FIFOs. As I mentioned, distributed RAM can be initialized during configuration so your FPGA can start with your memories preloaded. The write operation of distributed RAM is synchronous and the read operation is asynchronous. The RAM output can be connected to the flip-flops in the same slice to create a synchronous read. The two LUTs in the slice, as well as the LUTs in other slices, can be used together to form a larger memory, but this will require extra logic for the input decode logic and the output multiplexer logic to do so. Most customers are creating larger distributed memories with the core generator utility because it will create this necessary input decoder and output mux logic automatically. The caveat to making larger distributed memories is that the memory built will not be as fast as one built with a block RAM, so most designers opt for a block RAM implementation in this case. Designers sometimes like to initialize their memory without the use of the coefficient file that's used when designers build their memory from the core generator. To that end, customers can use the text I/O code in VHDL or add an initialization file into their HDL code if they want to infer the distributed memory resource already initialized. Virtex-6 block RAM is 36 kilobits of true dual-port memory. This means that each block RAM has independent read and write port widths, and that each port has its own clock and different read and write aspect ratios. Note that like Virtex-5, Virtex-6 block memory has embedded ECC or error correcting code logic. Virtex-6 also has dedicated FIFO logic that is also embedded in the silicon. The block RAMs include a configurable aspect ratio functionality which allows each block RAM port to have a customizable width. This helps the memory lend itself to more applications and ensures efficient use of the block RAM. For example, this means you can write to port A in bytes, plus use the parity bit, then read from port A serially with no access to the parity bit, and then also write to port B in 16-bit words, plus using 2 parity bits, and then read from port B in 32-bit words plus 4 parity bits. So there's really quite a bit of flexibility as to how you use your addressing of this memory when targeting the block RAM. Virtex-6 block memory also includes a pipelined register option, which improves the speed to up to 600 MHz. This architecture includes output registers that provide a faster clock rate, but the caveat being that it provides increased latency. Block RAMs are also cascadable, which means they can be connected together to make larger memories or FIFOs. Virtex-6 also has a byte write enable functionality that is helpful to embedded designers that are targeting embedded applications using the Microblaze soft processor core. As I mentioned earlier, you can load the block memory's contents during configuration with the FPGA bitstream, so if you reset the memory while it is running, you only clear the registers, not the contents of the block RAM. It is important for you to not violate the address setup time while the memory is enabled. Leaving the memory enabled while the address setup time is unknown might produce unpredictable results. So leave the memory disabled when not writing to the memory. This will also save you power. Finally, Virtex-6 includes Hamming error correction logic to fix bit errors. We'll talk a bit more about this feature a little later. Virtex-6 block memory allows segmentation of the block RAM into two 18 kilobit memories. The block memory cannot be segmented further. This assures efficient usage of the dedicated block RAMs to suit your application. In general, this is a pretty useful functionality since it allows you to not waste block RAM. However, it does push the user to make certain they take full advantage of the leftover block RAM. This means you might have extra memory that you can use for finite state machines or use for FIFOs when transmitting data between unrelated clock domains. So make certain that you try to think of out-of-the-box solutions because you might end up wasting block RAM otherwise. You should also note that unlike Spartan-6, Virtex-6 allows you to build a FIFO out of one of the segmented 18 kilobit memories, so that's also very useful. As I mentioned, these block memories are true dual-port RAMs. This means you have a ton of flexibility, and likewise, you need to make sure you're using them properly to avoid problems. You should remember that read and write operations are done simultaneously and independently on both ports A and B. This means that each port has its own clock, enable, and write enable ports. Every write operation also performs a read operation. This means that you have the ability to select the operation of the block RAM you want to use. So you can perform a read before write, a write before read, or not allow an output change from the block RAM when writing. This can all be selected when you build your memory with the core generator. It is also very important that you remember that you can perform a simultaneous read and write or write and write to the same memory location. Both of these operations can cause data corruption, so you will have to make sure that your address and control signals are stable during operation so you can avoid corruption. Finally, there is a list of the supported block RAM configurations shown here. These will be chosen for you automatically when you use the core generator, such as customizing the memory size within the GUI. Each port can be customized to have its own depth and width, again giving it a great deal of flexibility to the user. Most block memories are used for simple dual-port block RAMs. In this case, each port is assigned either a read or write functionality, which is a natural structure for FIFOs, again, which are very commonly built with block memory. When using a single port input and a single port output, the user is allowed to build with the widest implementation of 72 bits on a single block RAM. If you had segmented your memory into two 18 kilobit blocks, you would be allowed to build with a 36-bit data width. This flexibility enables the user to double the memory bandwidth per block memory. Now, parity bits can be used for parity generation, which is left to the user to encode into their initialization of the memory. But effectively, the extra bit width can be used for anything, since it is being stored in memory like any other bit. That is why each block is 18 kilobits, not 16 kilobits. So while there is no built-in parity checking logic, the extra space for you to store that bit has been allocated into the block memory's construction. You will still need the extra logic to check that your data is accurate if you choose to use the parity bit. This slide is just showing you the supported sizes for the block RAM resources based on your selection of the functionality for your memory, whether that is true dual port, simple dual port, or single port. So if you're trying to plan this out, you have the information right here. But most customers just build the memory with the core generator and evaluate their configuration later. After all, the core generator will build your memory from these predefined sizes no matter what. So if you want to build a larger memory that uses more than one block RAM, you can do so with the core generator. You'll just end up with multiple block RAMs connected together with some additional input decode and output multiplexer logic being used. You should also note that if you wanted to manually wire these block RAMs together for whatever purpose, you can find more information about each of these configurations from the Xilinx Unified Libraries Guide on our website. Virtex-6 block memories allow for two RAMs to be connected together with the dedicated routing resources or cascade resources. This is important because it enables you to preserve the timing associated with a block RAM, but is only allowed between two neighboring RAMs. You cannot cascade more than two RAMs. Also note that Spartan-6 does not have this feature. If you want to build larger memories than this, you can construct them with the core generator. CoreGen allows you to build larger memory arrays like the 128K, 256K, 512K, and larger arrays. And these will include many more block RAMs. However, this will require CLB logic for the input decoder and output multiplexer logic, just like it would if you were building a larger memory with Distributor Ram. Now, this implementation won't be as fast as a cascaded memory, but it does make it easy to build a larger array. The integrated error correcting logic, or ECC logic, corrects single-bit errors on outputs. It can also detect, but not correct, double-bit errors. This allows it to identify the address of the error when needed. This logic is dedicated in each block RAM and can be useful if you want to deliberately insert an error for testing purposes. This resource can also be used with external memory controllers built with a Memory Interface Generator, or MIG. This new feature allows you to deliberately insert errors in your memory for testing purposes. This is especially helpful when designers are building an external memory controller into the FPGA for use with a high-speed memory device. Virtex-6 supports the use of a byte-wide write enable, just like Virtex-5 does. This is useful if you are building an embedded application with microblaze, since Virtex-6 does not contain an embedded microprocessor. The byte write operation during write first mode makes the bytes not being written to show an undefined value on the output. That way the output truly reflects the new memory contents. You also need to remember that writing always implies a read, so if your design is always reading data from the block RAM, you may need to alter the design to only read when the read signal is inserted. Virtex-6 includes dedicated logic to convert each block RAM into a FIFO. This is of course going to have better performance than a soft-core implementation of a FIFO, and this will also save CLB resources since this logic is dedicated in the silicon. It is a full-featured FIFO that supports synchronous and asynchronous read and write clocks, so no phase relationship between the clocks is required. It has full empty and programmable almost empty and almost full flags. The synchronous FIFO mode eliminates the uncertainty of flag latency inherent with asynchronous operation. It also has an optional first word fall-through option that enables the first word after the empty signal is asserted to be immediately available. The FIFO offers many configurations, just like the block RAM, and it even is available to one of the segmented memories if the block RAM needs to be segmented into an 18 kilobit block. Note that the FIFO read port corresponds to the block RAM's A port, and the write port is assigned to the block RAM's port B. As I mentioned earlier, the block RAMs can be cascaded by connecting two neighboring block RAMs to make a larger memory. Well, now we're going to show you how the two block RAMs can be cascaded to make a 64 kilobit FIFO. On the left, the two RAMs and their dedicated FIFO logic have been combined to build a 512 by 144 FIFO. This does require some extra CLB resources to build the appropriate control logic, but it is easily done and is very efficient and fast. Likewise, a 16K by 4 FIFO was built with two block RAMs and their associated FIFO logic. Now this could be the same two block RAMs or two different ones, it doesn't really matter. All the block RAMs have the same ability to configure to different sizes. All of these configurations can be built when you build your FIFO with a core generator, that is the utility commonly called the FIFO generator. CoreGen includes a GUI option to build a FIFO with the dedicated resources or build a soft FIFO that would use additional CLB logic. One of the nice things that the FIFO generator does is allow you to build a FIFO cascadable for width or depths as shown in this diagram. This chart shows you the amount of available memory resources for each density of Virtex-6 device. First of all, the amount of distributor RAM is nice to know, but not very relevant because, as I mentioned, most customers that use this configuration of the LET are building DSP applications, and that's simply not every customer. Most customers that are building DSP applications are using the system generators I mentioned, and that would allow them to determine how many LUTs their design would need. And since that kind of design work is done very early in the design flow, a customer would have little difficulty anticipating how many LUTs their design would need. In the end, most customers are much more concerned about the number of available block RAMs that their FPGA has. As you can see from this slide, Virtex-6 devices include as few as 156 block RAMs and as many as 1,064 36 kilobit block RAMs. The easiest way to determine how many RAMs you will need is to build each memory early with the core generator. That utility will easily show you how many block RAMs each of those components will need. Now, let's take a short quiz and try to find out what you've learned so far. Don't forget, it's a quiz. Have fun with it. This is not college. As I mentioned, the ISE tools support the use of the soft memory controllers with the MIG utility within CoreGen. This is best for all applications except embedded applications. Embedded applications should use the EDK tools, which give you the ability to add memory controllers when you add the multi-port memory controller component. This is also often called the MPMC component. Like the MIG, it is a GUI-driven utility that makes optimizing your controller for embedded applications very easy. EDK will allow you to customize the controller and attach this component to your system bus without you even having to instantiate the component in your HDL. The MIG allows you to customize the memory controller features, data rate, bus width, memory component parameters, I/O bank assignments, and also generates the necessary RTL source code for instantiation. You will note that the MIG also performs all the necessary error checking to make sure that you are designing appropriately for the Virtex-6 architecture or whichever FPGA you target. The MIG will store your pin constraints in your design's UCF file. In case you're not familiar with this file, the UCF is the designer's user constraints file. All design pin assignments and pin attributes are placed in this single file. It is then used by the implementation tools when building your design. Currently, the MIG supports DDR2, DDR3, QDR2, and RLDRAM2 memory controllers for the Virtex-6 device family. Note that different controllers are supported for different device families depending on the ability of the device to meet the typical performance required of the memory standard. However, it is often the case that as a new device is introduced, it takes a little time for all the possible supported memory controllers to be supported for that device within the MIG. So just be sure you update your MIG utility periodically to get the latest cores, or call the hotline if you might need another controller that's not shown within MIG. The standard FPGA design flow still applies with the use of the MIG. First, you will need to open CoreGen, and from here you'll start the MIG. Then you'll choose the controller you want to build, customize it with the GUI parameter settings, and generate the core. This will generate your controller's RTL and UCF files. Again, the UCF file is your core's associated timing constraints and pin assignments. You'll then instantiate the controller into your HDL. This will be done by copying the generated instantiation templates if you're working with a third-party synthesis tool, or if you work with XST, the instantiation templates will automatically be added to your ISE project. After building it, you should always complete a behavioral simulation to verify that this controller meets your system needs, and of course this is supported. You then need to perform a behavioral simulation of your controller and verify that it meets your needs. After you have decided that this controller is what you want, integrate your UCF file into the overall design's constraints file. Import your source RTL, synthesize, and finally place and route the design with the implementation tools. Note that timing simulation is still supported and encouraged, but it is not required. Lastly, verify your design in hardware, probably with one of our demo boards. This slide just shows you a couple of screenshots from the MIG. In the end, you will have 6 or 7 GUI screenshots to customize your memory's parameters, customize the I/O banking for your controller, and set various options. The controller also has some debug and IOB options that will affect your controller's speed and power consumption on the physical layer, and these can all be set from within the MIG. One of the more elegant features of the MIG is to gray out restricted columns of IOBs for your device. This assures that you make a suitable controller for your density of device. And as always, the MIG does most of the error checking for your controller before you integrate the component into your design. As I mentioned, the MIG will make a UCF file for your pinout and clocking constraints. It will also make the necessary RTL files, which are unencrypted for you and can be edited by the user. There is also an HDL simulation folder that is necessary for behavioral simulation support. We now want to take a couple of minutes and tell you about some of the new features of the Virtex-6 memory controllers that are made with the MIG. The performance of the Virtex-6 base controllers for the DDR3 and DDR2 is half the memory system frequency. This is possible because the memory specification does not require commands to be issued at full frequency for the DDR2 and DDR3 standards. Likewise, the state machine to process the commands can be run at half the frequency of the memory system. This makes meeting your timing needs significantly easier. For example, a 500 MHz based memory system needs only a 250 MHz controller state machine. This allows us to build controllers in lower speed grade devices at higher frequency than we could have done with a full frequency memory controller. In addition, the new controller has the capability to reorder commands for a more effective data bandwidth utilization. This is very important because we cannot afford to simply crank up the clock frequency and get more bandwidth by brute force. In some systems, if the controller is not effectively using the data bus, the actual bandwidth can drop to 10% of the maximum capability. This is because if the commands are a string of read-write, read-write, the bus turnaround time will introduce a lot of dead states. And if the read or write commands are not accessing existing open rows, the pre-charge time can also add dead states. These dead states, or gaps, in the data bus are a consequence of the nature of the way DRAMs operate. To get the maximum bandwidth, the controller needs to minimize the read-write, read-write type of accesses and also maximize accesses to the open rows. We also wanted to take a couple of minutes and give you some guidelines on how the memory controller should be laid out in Virtex-6. First of all, don't forget that all of this information is included with the MIG user guide. If you're using the DDR3 memory controller, be aware that the address and control bank must be in one of the center I/O columns. In this example, we see the address and control pins located in bank 25. Likewise, the data pins are required to be relatively close to this bank. In fact, we suggest the data pins be placed in I/O banks within one column and one row. In this case, that means they must be in the banks located in the red square you see on the slide. This, of course, because of the performance constraints associated with the DDR3 controller. By keeping these pins close, we can assure the necessary performance. One of the nice things about the MIG is that it contains a bank selection GUI that incorporates these kinds of rules and ensures success. Now, let's take a final quiz to verify what you learned and that you learned as much as you could about the new Virtex-6 memory resources. In summary, Virtex-6 contains distributed memory, which is good for fast localized memories and small FIFOs. It also has dedicated block RAMs, which have an associated dedicated FIFO logic for easy conversion of each block RAM into a FIFO. This provides a bigger on-chip memory resource. It also has embedded error correcting code, or ECC logic, that is associated with each block RAM. And these both are great for mid-size buffering. There is also support for soft memory controllers, and this is incorporated with the MIG, or Memory Interface Generator. This allows you to build soft memory controllers using standard CLB logic and provides support for fast connection to popular standard RAMs. This is ideal for the case a customer is working with a large off-chip memory component. The memory components, that is, those that use the FIFO, the block RAM, or the distributed RAM logic resources, are easily built when you use the core generator. Well, there is lots of useful information about memories and memory controllers that can be found on Xilinx's website. The Virtex-6 user guide provides very helpful and detailed information about the distributed memory and block memory resources included within Virtex-6. All Virtex-6 users will probably want to refer to the document for the most silicon information. The Virtex-6 FPGA Memory Interface Solutions user guide is also a very helpful document. It includes a description of all the supported controllers, supported vendor devices, and the necessary parameters you'll have to assign with the GUI. It also walks you through the various settings that can be made with the MIG and describes all the necessary planning you should do when targeting different memory controller standards, including pin planning and supported memory configurations. If you would like to see what other courses we offer or what other free RELs are available, you should go to the Xilinx education link you see here. I would also like to mention again that there are other architecture modules available that discuss the basics of Xilinx's newest devices. You may find these helpful, especially if you want to learn more about the differences between the available FPGAs. But whatever you do, please take a second and let us know what you thought of this REL. Just click on the icon on the next page and tell us what you think. Again, my name is Frank Nelson. You have been listening to the basic FPGA architecture module for Virtex-6 that describes the available memory resources. Thanks for listening, and again, thank you for your business.